Okay, next speaker is Li from riken. The title is Measuring Controllability of Chaotic Systems with Deep Reinforcement Learning.
Hello, everyone. My name is Li from riken. Today, I'm going to present a recent work measuring the controllability of chaotic systems with deep reinforcement learning. So our long-term vision is to control typhoons, that is to say, to weaken the intensity or slightly push the tracks of typhoons away from the land so that the damage to human beings is less. And let me start from some basic picture of the typhoons. Typhoons are the biggest and most devastating storms on Earth. Spans of hundreds of kilometers wide, 10 to 15 kilometers tall, and all the way to the tropical poles. And as you can see, there's a very complex structure, and but as a simple model, which is the work by Professor Kerry Mano, we can think of this very complex structure as a heat engine that converts heat into mechanical work. And the heat source for the engine is the moisture from the ocean, and the heat sink is the radiation into the outer space. And if we calculate the input energy to the heat engine, it is roughly on the order of 10 to the power 13 or 14 watt. But the best technology by human beings is roughly 1 gigawatt, which is 10 to the power 9 watt. So there's a gap of 3 to 5 orders of magnitude difference. And this is one of the major difficulty in achieving the vision. And for that, I very much like the metaphor of Achilles' heel. So Achilles is a nearly invisible warrior, but he has one singular vulnerability, which is his heel. And despite his strength, Achilles was shot down by an arrow on his heel. And I was thinking typhoons, although it has immense power, it may also have some weak points. And our goal is to identify such its vulnerability in typhoons. And this is a very hard task, but it is also a very, very interesting scientific challenge. For this purpose, we use the method of deep reinforcement learning. At the core of the deep reinforcement learning, there's an agent interacting with the environment. So the agent observes the environment and it gives an action and receive the reward from the environment. The agent will learn and optimize itself to maximize the future reward. And here I would like to show a demo. I would like to show a demo by DeepMind that has amazed me from time to time. This is the game called Breakout. The goal of this game is to move the board left or right, not to miss the ball, but also to reflect the ball to hit the blocks of the wall. And they use the deep reinforcement learning to train the agent to play the game. After 100 episodes of training, they seem to find some clue, but most of the time it does not succeed. But after 400 episodes of training, it basically can get the ball all the time. Something magic happens after 600 episodes of training. It finds a very smart way to hit the blocks, which is to make a small tunnel on the side edge of the wall. So the ball can reflect inside the top space and hit many blocks in a short period of time. So in a sense, it finds the Achilles heel of this game. And what we are hoping for in the future is that to apply the deep reinforcement learning to the typhoon control problem and find the Achilles heel of the typhoon or the vulnerability of typhoon. Up to now, we have tried to apply this method for 3 tasks. The control of chaos in Lorentz system, the suppressive genesis in typhoon, and the weakening of mature typhoons, and all by relatively small perturbations. And all the results are very preliminary, and we treat this as a test of the method itself, not for practical control. And in today's presentation, I will focus on the Lorentz system due to the time limit. So this is the Lorentz system, a famous chaotic system. Lorentz system is a simplified, really Bernard convection system. So a system which is heated from the below and cooled from the top. And we have the equations for x, y, and z. X, y, z correspond to state values of the system. For example, x is the rate of convection, y is the horizontal temperature variation, z is the vertical temperature variation. And sigma, rho, beta are parameters for the systems. And then I apply the deep reinforcement learning to the system. And the goal is to apply very small perturbations to x, y, and z at time steps of the system in order to control the system to stay on the right branch of the system rather than swing right and left like a butterfly. And I give the reward +1 if the system stays on the right, and gives reward -1 if it's on the left. And by interacting with the Lorentz system, the agent gradually learns how to control. Initially, the system stays longer on the right, but still visits the left. After extended period of training, the system can stay on the right forever. And so the control is successful. And because we care about the size of perturbation, I further add a penalty to the reward. The penalty being proportional to the size of the perturbation. So in order to get a higher reward, the agent need to find smaller action at the same time of achieving the goal. And the result is a bit surprising. So the system finally converts to a single point. It's a bit hard to see, so I put an error there. And so the system converts to that single point, and the size of the action converts to almost 0. This to me, initially, it's very, very surprising. So how is that possible? It turned out that the deep reinforcement learning agent automatically finds the fixed point. The fixed point is the place where if you stay there, it will stay there forever. And for an unstable fixed point, you just need infinitely small energy to keep it there. Therefore, the fixed point is the theoretically most efficient point. And please note that we give no information about where is the fixed point to the system. And the result implied that the deep reinforcement learning can indeed find extremely efficient control strategy. Next, I'll talk about measuring the controllability with the deep reinforcement learning. So this research comes from the question raised by Dr. Miyoshi when we used deep reinforcement learning for typhoon genesis. So here is we can see an orange curve, which is the uncontrolled typhoon, which developed into a strong, mature typhoon. And the blue curve is the typhoon under no control, under control. So the typhoon genesis is suppressed in this case. And the question is, where should we start to apply the control? For three possible timings, A, B, and C. Should we apply control start from A, or we start from B, or we start from C? A is probably too early. If we apply control here, the energy is being wasted. C is probably too late. If we apply control there, then we cannot achieve the goal. So in other words, at time A, the control is not needed. At time C, the control is not effective. So two aspects of controllability naturally arise, the necessity and effectivity. And here we use the Lorentz system to study controllability, to study these two aspects, because it requires less computational power. In traditional control theory, the way to measure controllability is by the Lipnov exponent. The Lipnov exponent measures if we give a small perturbation, it tells us how fast the perturbation grows. And the idea behind this is intuitive. If the perturbation grows fast, then it means we just need a small control signal to have the big effect, which in turn means it is easier to control. Here I calculated the Lipnov exponent in the Lorentz system. The color here represents the magnitude of the Lipnov exponent. Red means it's positive, meaning the perturbation is growing. And blue means negative, where the perturbation is shrinking. And here you can see a very interesting pattern where in the upper part, the Lyapunov exponent is negative, and in the lower part, the Lyapunov exponent is positive. This is very natural because at bottom center, there's a saddle point, and near the saddle point, the trajectory will diverge. I'll simply skip. But there are two fundamental limitations in this method. First, basically the goal of the Lyapunov exponent is to find the largest change in the whole state space. And it's very hard to define what is good region, what is bad region. And second, it is hard to consider continuous perturbations. Here we propose controllability measurement using the framework of the deep reinforcement learning. This is the framework. So here is the framework of the deep reinforcement learning. The actor here is the policy function. It tells what to do if it receives an observation. And here is the value function. Value function measures it's an estimate of the future reward shown by this formula. And in this formula, the capital R is the reward of each time step, or how good the goodness of the current step. And the value function estimate the discounted summation of the future reward by a factor called gamma. Gamma is a factor between 0 and 1. Gamma is setting basically how far we can see. Gamma equals to 0 means we only care about current step. If equals to 1, it means we care about infinitely long future. In practice, we should set it to how far we can predict into the future. And here I choose gamma equals to 0.99, which corresponds to 100 steps of a full cycle in the low-range system. So let me show you how is the value function being updated in the deep reinforcement learning. Initially, the value function has no knowledge of what is good, what is bad. So the estimation of every state is basically 0, which is shown by color blue. After some training, the value function starts to understand the good and bad. And so it shows on the right, it is red, it is positive. On the left, it is blue, it is negative. But what is most interesting is that there's some region in the right, it shows blue. So although it is in a good region, it understands that it will soon turn into a bad region. It means that in this region, the control is not effective anymore. In other words, this measures the effectivity of the control. And this is the one after a very long time training where the value converges, and it shows a much finer structure of the value function. And this is the value function under control. I showed the same figure before. And this is now I train another agent where I intentionally set a control to be none. So this time it measures the goodness of each state without any control. So we get this interesting figure. If we focus on the right branch, we see there are clearly different regions. Inside, near the center, it's red, meaning it is good even without control. In the outer region, it is blue, meaning it is bad without control, meaning we need the control. And so the blue measures the necessity of the control. And the difference between the two is interesting. In the center, both are red, meaning with control or not, it is good. In some slightly outer region, this is red, this is blue. So it means there's improvement by the control. And if we go very out, both are blue, meaning whether or not we apply the control, the situation is very bad. And by calculating the difference, we get this figure. And we can see there's a range structure appearing that corresponds to where the control can improve the value function most. And that is the region of the best control position. So in summary, we have shown that the deeper reinforcement learning can identify highly efficient control strategies, and we also propose a two-dimensional measure of the controllability. That's the end of my talk. Thank you very much.
Thank you very much. Are there any comments or questions?
Yeah, maybe we need to learn from your finding. So how to apply this to typhoon controlling typhoon? How do you apply this idea to control typhoons?
So in typhoons, we need to define what kind of action space. For example, if we have some perturbation method device, which is cooling SSD in some region, and we can set the action space to be where the device moves to. And it will automatically learn where is the best position in order to maximize the reward. The reward, we can set it to be how much the intensity being reduced. And it will update itself to learn what is the best way to reduce the intensity.
So the normal numerical simulation model can be applied, your technique can be applied directly to the numerical simulations of typhoons.
Yes. So if we look at the diagram here, so the agent is the neural network that is being updated, and the environment is the agent trying to maximize, to optimize itself for. So we can use the simulation for this environment, and it will learn to how to interact with this environment. Thank you for the question.
Thank you very much. So it's time. So let's move on to the next. So thank you very much.